In this example, we're going to examine the changes in potential energy as well as kinetic energy that a rock experiences as it travels from some higher height to a lower height. So let's look at the following example. Suppose the original height of a rock is 10 meters. And now we want to calculate the rock's speed when it falls 5 meters from its initial height of 10 meters. Now let's assume the mass of our object, the rock, is 5 kilograms. So let's diagram our problem. So our rock is at an initial position of point 1, 10 meters above the ground. Our final point, position 2, is the rock 5 meters from its initial position and 5 meters from the ground. So this is our position 2. We want to calculate the speed of the rock at point 2 when it's midway between the top point and the lowest point, our ground. Now we're going to make the assumption that no air resistance exists, and that means if we're neglecting air resistance, which is a non-conservative force, we can say that our mechanical energy of the entire system is conserved. In other words, it stays constant. So if we add up the kinetic energy plus the potential energy at point 1, that equals the kinetic energy and the potential energy at point 2, which can be expressed using the following formula, where these 1's simply mean our position 1 and these 2's simply mean our position 2. So our sum of kinetic energy plus potential energy at point 1 is equal to our sum of kinetic energy and potential energy at point 2. So let's begin. What's our initial velocity? Well, our initial velocity is 0. Our object, the rock, is dropped from this point 10 meters above the ground, so its initial velocity is 0. That means this v is 0, and that means this point, this amount is 0. Our rock has no kinetic energy. Now, our initial gravitational potential energy is mgh, where the h is simply our 10 meters. And this equals the kinetic energy at point 2 plus the potential energy at point 2. Now, there is some velocity, and we want to find what that velocity is. So, let's notice that on each side we have one m. An m appears here, an m appears here, and an m appears here. So that means we can cancel them out. And that's exactly what we get in this step. And now we can basically bring this term on this side, multiply both sides by 2, and take the square root. And we get the following formula. Because remember, we're solving for this velocity at point 2. We want to find what the speed or the magnitude of our velocity is. The direction of velocity is simply directly downward. It points in the same direction as the force of gravity, which points down. So we get this formula, and now we simply take our calculator, we plug in our values because we know what g is, 9.81 meters per second. We know what h1 is, 10 meters. We know what h2 is, 5 meters. 10 minus 5 is 5. 5 multiplied by 2, which we got from this 1/2 term. When we bring the 1/2, we get 2 on this side. So 2 times 5 times our g, our gravitational field, 9.81, and we get 9.09 after we take the square root. So our object is traveling with a velocity downward and a speed of 9.09 meters per second.